So let's have a look at the different distance measure or distance measure functions or algorithms that are available for evaluating vector searches and being able to identify vectors that are similar to one another. Now, the main list of distance measures are Euclidean distance squared, cosine similarity, right? That's the kind of the main one that you'll come across, and that's kind of the default one that you'll find in most vector databases and so forth. But some of the other ones then are to do with dot product, Manhattan distance, and Hamming. Now, the cosine similarity is the most common one because it's the simplest to do, and the results are pretty good. But maybe depending on the type of data that you have, some of the other ones might be more suitable. Okay, now you won't really know this unless you do some experimentation, and when you do that experimentation, you need to ensure that that's actually included within your applications and your querying of the data, so your developers will need to know. As I've mentioned previously, is that we don't necessarily have to know the ins and outs and the technical details and the math behind each of these different algorithms, because other people have worked it out for us, and being able to know which one to use, knowing the maths doesn't really apply, because what we need to be able to do is, do we have a bit of an idea of what it actually does, right? So like I said, is what a sum function does, an average function does, a divide does, a standard deviation does, all of those kind of functions. You might not actually understand the math behind it, but you know how to use it and what it gives us. Okay, so let's have a quick look at each of these particular ones. So the first one, which is kind of the default one, if you want to say that, for an awful lot of kind of machine learning distance measures, results is the Euclidean distance. So this is effectively a straight line between two different vectors. Okay, and this is based on the Pythagorean theorem, where we kind of complete the triangle and being able to measure that distance. And the shorter the distance that's there, the more closely that they are related to each other, and the bigger the value, the less similar that they are. And we can see some of the mathematical functions that's there. Okay, so you don't have to do those calculations or anything like that. That's automatically done within the database for you without you having to worry about it. Now, a variation of that is to do with Euclidean distance. Now, if we kind of just go back to Euclidean distance, it's to do with, see that square root on it, is that, well, if we don't do the square root, we do the square root of it, which gets rid of the square root. It's kind of a simpler calculation that needs to be done, right? Which means it's a little bit faster to calculate. So that might be actually useful to you. So sometimes when you're using Euclidean distance, the database may have actually implemented the squared rather than the actual kind of original kind of formula on it. But the cosine similarity is this is the most commonly used one, and what this tries to do, it looks at the measure of the angle between the two vectors. So the larger the cosine, the closer the vectors, the smaller the angle, the bigger the cosine. So the cosine similarity measure, it looks at the similarity in the direction or angle of the vectors, ignoring kind of differences in size. Now, as you can see, is that can be kind of useful for some data, but in other data, the size of the vector, right, the magnitude of the vector does become important, because if it's we may have a small angle, but there could be kind of very different sizes, right? Now we'll have a look at kind of other things that can actually apply to that. So the smaller the angle, the more similar they are. The bigger the angle, the less similar they are, and we can get values kind of coming out based on those. But this is the one that's kind of most commonly used. Again, just like with all of the algorithms, there's advantages and disadvantages of some of these. All right, so if we kind of think of the magnitude of it, the previous ones, Euclidean distance ones, take into account some of that kind of magnitude size, based on the distance, where cosine is really just about the angle. The next one looks at to do with the dot product, and what the dot product looks at is the similarity between the vectors by multiplying the size of each vector by the cosine of the angle. So a bit more of a calculation involved in this. So the larger the dot product, the closer the vectors are to one another. And part of this, what it kind of looks at, it kind of drops the angle from one particular kind of vector onto the other one, and being able to multiply out the resulting kind of vector sizes in relation to that. Bit more calculation on it, but kind of it depends on the type of data you're actually working on. The next one is to do with, it's called Manhattan. So it's like, like the map of Manhattan in New York, is how do we get from one point to another point? So what's the shortest distance that we can go between it without going in a straight line? So this is where like you're following traffic to be able to get it, or you're kind of doing a walking route, like Google Maps kind of thing, in order to be able to calculate out what is the shortest number of steps that you need to take to go from one vector to another vector. All right. So a straight line would be kind of the simplest, because that has the fewest number of steps on it, but in most cases it's going to involve multiple different steps. And then the last one that you'll see kind of used quite a bit is to do with the Hamming similarity. And what this effectively does, it does kind of bitwise kind of operations on it. And what it looks at, it looks at the kind of a bitmap of all the values within your vector, and look at, well, if I did the XOR on it, is that, what are the things that are similar and what are the things that are dissimilar? So if we have two vectors that are kind of vaguely like each other, is that, an awful lot of those vector values are going to be the same or very similar. So we can actually just remove those, and you're left with just the vectors that are different. And the lower the value of it, the more likely that the vectors are kind of quite similar. So this can be quite a fast, efficient way of being able to compare different vectors. So that's all the different kind of distance measures that are typically within vector databases. And in the next video, we're going to have a look at some of the different indexing methods that are available within vector databases.